Christina. I was hoping I could get this to you earlier. I think you're probably pretty close to starting that AP test. I think it's in the afternoon. Just wanted to give you some feedback on the sheet. See if I can get some marks going. Maybe, maybe not. Maybe this will do. Okay. I've got in pink right now as far as masses. I don't think they're going to be used on the test. If they might include these for momentum of particles, but I doubt it. So momentum, mass times velocity. Maybe, maybe not. Speed of light, we didn't cover. Electron charge, magnitude, Coulomb's law, we didn't cover. You've got the green light on the green stuff, which is good. As far as electricity, clearly we did not do that in class. We didn't even do waves, so get those out of there. As far as the yellow, right, this is just chapter 4 thing. It's just a different way to write Newton's second law. The net force equals mass times acceleration. They just like to have acceleration shown. Second yellow, this is the equation for momentum. That's chapter 7. Mass times velocity, so it's directional and has a magnitude. Right here, this has to do with impulse. Both sides, you can quantify impulse. Impulse, right, that momentary hit, right, is a force applied over a period of time. So an impulse is a golf ball being hit by a golf club, an intense force over a short period of time, force times delta t. Well, that's going to cause a change in momentum of that golf ball. Baseball, pitcher pitches the ball, right? The impulse of the bat on the ball, short period of time, intense force, is going to change the momentum, right? The delta P of the baseball. So you can quantify impulse by measuring the change momentum. If I know the change in momentum and I know how much time, right, I can figure out the force that was applied to the object. As far as the delta E and work is equal. Like if I apply work is a transfer of energy into or out of a system. So think of that pendulum, right? The bowling ball. If I release the bowling ball, it swings away and it comes back up about the same height, right? If I push on that bowling ball, right, it's going to swing away and then it's going to come right back up. I applied a force times a distance, okay? And that is work. And so if I do work on a system, I add energy. And if the system does energy or does work, like the bowling ball in that bowling ball pendulum hits a box, it applies a force, right? That's an impulse, right? It applies a force over a certain distance. It will take work or energy out of the system, okay? Now this force times d cosine theta, that's trying, if I apply a force at an angle over a distance, right? They're trying to find the most effective force or the cosine theta. So force parallel to the displacement. P is for power, and that is how much the rate at which you use energy, right? So if I change the height of something, maybe using a lift, right? How much power is used? Well, how much energy did I transfer? Did I go up 10 stories, right? Over an hour, or did I go 10 stories over 30 seconds? That's the rate at which energy has been, or rate which you've had a change of energy. Okay, so that can be applied to change of kinetic energy also. This X, a cosine, I don't anticipate you using this because ultimately it looks like a cosine wave. Okay, and that has to do with periodic motion or simple harmonic motion. You're going to have, as far as position versus time, right? If I look at a position versus time graph, where is my maximum velocity? Well, I'd look at the slope of this graph. Okay, where's the minimum velocity? At the peak. So if you were to think about a spring oscillating to a top, to through equilibrium and back through its base at the top, zero velocity, right? Maximum potential energy, minimum kinetic energy. Through equilibrium, maximum velocity, so maximum kinetic energy. And then at its low point, that at that point is we're going to have minimum kinetic energy. So that's all that is about. This A, right, this alpha equals net torque over I, which is rotational inertia. That's just a different way to write Newton's second law, but that's applied to a rotating object. So if I apply a torque to a disc, so let's think of a merry-go-round, like kids are sitting on the merry-go-round, I apply a torque, a force at a radius, I start that merry-go-round spinning, correct? Right? That merry-go-round has a resistance to rotation, that rotational inertia. I can calculate my angular acceleration if I know my torque and I know my rotational inertia. Alternate ways to calculate torque, right, is radius times that force. But the sine theta is you're trying to find the effective force. The effective force. So if I have a bar and I apply a force at an angle, this is why I don't like sine theta. I'm trying to find the force that's effective in rotating it. Now, if I find the component that goes through the axis of rotation, does that help? No, it just compresses the bar. But if I find the component, right, that rotates it, I have to find the component that's perpendicular. So that's why they have this, what's the right word, sine theta. But it depends on where you put the theta. You got to find the force that's perpendicular to the radius arm. Okay. When we go down these red items, L, that's your angular momentum. Okay. I, or the rotational mass, rotational inertia times rotational velocity, angular momentum. And so change in angular momentum is caused by a torque applied over a period of time. Similar to that merry-go-round, I apply a torque, a force at a radius, for a certain period of time, I am going to get, right, a change in angular momentum. Okay. You've got K for rotational kinetic energy. It's yellow. If I want to quantify the kinetic energy as something is rolling, for instance, if I spin that wheel, right, the merry-go-round, is it translating? Is it translating through the park from point A to point B? No, it's just spinning. But does that kinetic energy, that rotational kinetic energy, have the ability to do work? Absolutely. So rotational kinetic energy applies. This is a force of the spring. Now, what is up with those absolute values? A force is a magnitude and direction, okay? In physics, they have ideal springs that can be compressed a certain distance or extended a certain distance. So that distance is called x, right? If I compress it 5 centimeters, it takes a certain force to do that. If I extend it 5 centimeters, it takes the same magnitude of force to get it that distance. The absolute values are basically saying magnitude only. So if I compress it 5 or I extend it 5 centimeters, same force. That's what the absolute values, magnitude. You've got the potential energy of a spring, so 1/2 kx squared. And this is density. I don't know if they've got density on this because I don't anticipate using it. This is delta U. So this delta Y is just, it should be, I'd call it MGH. But they're basically saying it's a change in the Y position. Okay. Period and frequency, knowing that period is the inverse of frequency. And then if you've been given rotational quantities, this is a shortcut to do it. These results, right? These results as far as T sub S, that's the period of a spring and what influences the period of the spring, the mass, right? And the K factor, not the displacement of how much you stretch it. It still has the same period, essentially. And then for period of a pendulum, that's a subscript P. What influences the period of a pendulum? The length of the pendulum and the gravitational pull of the pendulum. Those are the only two things. So I tried to summarize those in the video for pendulums. As far as the rest, force of gravity, right? They just put this acceleration off to the side. Force of gravity equals mg, okay? So it's just rewritten. And this potential energy, this is in terms of the gravitational constant. So it's essentially mass g using gravitational, right, and h. The gravitational, I guess, quantity in terms of big G, right, is going to be little g equals mass of the planet times big gravitational constant, and then it's going to have this radius squared. So if I have an object, mass 1, times little g, but in terms of universal gravitational constant, that's the mass of the planet, or m2, times big G divided by r squared, and then that height is that radius between them, which is r. It essentially reduces down to that. So we didn't do that in class, but it essentially is mgh, but utilizing the universal gravitational constant to rewrite that. So this is going to be potential energy of a satellite, okay? Way off the planet, surface of the Earth, it's going to have a different G value, and so on. So I know this is quick. I know it was messy. I don't know when your test is started. I lost track of that somewhere, but I'm hoping this video will help you, okay?